Okay, so yesterday's homework, you were supposed to do the first 4 problems on the sheet that I handed out to you. Today's homework was 5 through 10, but I didn't really realize that 5 and 8 were the same. So 5 and 8 we're going to do as one thing. I'm not going to give you credit for 2 problems that are the same. Okay, so we're going to do 5 and 8 to start with. Okay, and all this is about figuring out whether molecules are polar or nonpolar. In fact, one of these molecules kind of go beyond the scope of what we've already learned in here, so we'll make that one extra credit. Okay, won't count against you, but if you happen to get it right, because it's kind of something we haven't covered yet, I'll give you some credit for that. Okay, so starting with 5 and 8, that would be SF2 is the molecule I gave you, the formula for the molecule I gave you. Okay, if you do, I'm not going to go through the electron dot notation for these, all right, and the sharing arrangement. We've done that enough in Unit 3. Hopefully you can do that. I'm just going to start with the Lewis dot formula. Okay, so sulfur will be the central molecule, and fluorines will be attached to that. I put the fluorines on the right and the bottom. The fluorines could be, instead of on the bottom, to the left, or instead of the right on the top. That could be on any 2 of the 4 sides. Doesn't really matter which one. Regardless of whether you put them there, you're still going to get the same electron pair shape, where you just look at the sets of electrons around the central atom. Now, a set is one of 2 things. Lone pairs are a set, so there's 2 lone pairs. And all the electrons shared between 2 atoms make up a set. And there are 2 of those. There's a set here and a set here that are shared between sulfur and fluorine. So that's 4 sets, and that's always going to be a tetrahedral. And the electron pair shape just means we put those electron pairs out there on the end of that. From there, then, we're going to make a modified electron pair shape in this case, where we replace sets of electrons with the atom symbol for the atom they're shared with. So there's only 2 of these that are shared. We're only going to replace 2 of these sets. And so we call that a modified electron pair shape. So electron pair shape, modified electron pair shape. Both of these are tetrahedral. Okay, so you got 2 names. One's the geometry, tetrahedral, and the other is the type of shape we're trying to draw. This would be the electron pair shape. This is the modified electron pair shape. From this, then, we're going to do the molecular shape. And whenever you finish getting rid of all the electron pairs, you'll have a molecular shape if you follow the procedure I've taught you. So we're going to redraw this exact same drawing, same angles. We're just going to get rid of the lone pairs. And so now we have a molecule that we call bent. Its geometry is bent. This is the molecular shape, so this is called a bent molecular shape. Anytime you have to get rid of a set of lone pairs as you go from a modified electron pair shape to the molecular shape, if you have to get rid of a set of lone pairs, you're going to have an asymmetrical molecule. Now that's important for figuring out whether you have a polar molecule, but it's not really this molecule being asymmetrical that tells you whether the molecule is polar. What we're looking for really is asymmetry for polarity. So we also know about the bonds here. Got a question?
What if you went from step 1 to step 4?
You went straight from here to here?
Yeah.
Well, great if you can do that. I'm not going to actually even grade these. That was Unit 3.
Okay.
What we want to do is be able to get to this and get it right. If you leave off the steps and get this wrong thing, everything's wrong. Okay? So if you can't take shortcuts, don't. If you're not absolutely, positively, without a doubt, sure, don't take shortcuts. Do everything. Okay? I give you all those steps in between to help you get the right answer every time. Okay? So if you're not ready to do that, don't. All right? You'd be like jumping out of an airplane without your parachute. All right. So just because this is an asymmetrical molecule doesn't tell us that it's polar yet. We need to know about the polarity of the bonds. if the molecule is asymmetrical, not symmetrical, asymmetrical, then if the bonds are also polar, then the molecule is going to be polar as long as the bonds are all the same. Okay, if you have three things, asymmetry, if you have polar bonds, but all the bonds are the same kinds of bonds, then it's polar. Okay, so let's try to see if we can figure out what the polarity of the bonds will be, and for that we need our periodic table with electronegativities, and we can see that fluorine's electronegativity is 3.98, sulfur's electronegativity is 2.58, and that's the only kind of bond we have between sulfur and fluorine. So our electronegativity for fluorine is 2.98. I'm sorry, it's 3.98. 3.98. And the electronegativity for sulfur is 2.58. And what we're going to do is define the difference. We want the electronegativity difference for a sulfur to fluorine bond. Alright? And so the electronegativity difference is 1.40. If it's a molecular compound and the electronegativity is greater than 0.5, then that's going to be a polar bond. Okay? We know it's a molecular compound because we're combining all nonmetals. Okay? Alright, so now we know that the bonds are polar, the molecule is asymmetrical, all the bonds are the same. This is a polar molecule. So that's our claim that it's a polar molecule. The justification is all the bonds are the same. All the bonds are the same. That's A. B is the molecule is asymmetrical. And C, the bonds are polar. What? No. But I'm just letting you know that's how you justify it. Okay? We spend a lot of time trying to help you be clear about claims and justifications. Okay? Claims and justifications, they're very important. Not just in science, in almost every endeavor. Okay? If you're going to be a lawyer, you're going to be doing a lot of claim and justifications, trust me. Now, let's take a look at the bonds and a little more information about this. This is all you need to have. Really, for this problem, to get full credit, all you have to do is to show the shape of the molecule, because that's part of what you have to have to show me that you know what you're doing. So if you have the shape of the molecule right, that's a point. Okay, for the shape of the molecule, you're going to show that it's. You don't have to say that it's a bent molecule, but you're just showing that it is bent. All right. In order to say that it's a polar molecule, you have to have a reason why. Okay, so you have to show that the bonds are polar. All right, so we got bonds are polar up here somehow. 1 point for the bonds being polar. Okay. I'm sorry, that's polar molecule. Let's say the bonds are polar. Somehow you have to show the bonds are polar. Okay. Well, how would they know the bonds are polar then? Did they show the electronegativity difference in any way? Then they don't. That's not their argument isn't justified. Okay. You have to justify your arguments in here. We're in a science class.
So what you do here to differentiate, how do you know?
What you're looking for is whether or not the molecule itself has an asymmetry in polarity. That is to say, the polarity is unevenly distributed around whatever atom you're interested in. In this case, sulfur is the one we're interested in. Well, let me show you this. Here's another way to show that. Since fluorine has the greater electronegativity, and it's a polar molecule, fluorine has a greater electronegativity, we can use these dipole arrows here to show the electronegativity flows in that direction. Okay? So by seeing this, you don't use those dipole arrows if your electronegativity difference is less than 0.5 or 0.5 or less. Okay? But because they're greater than that, we can see that this is, I can look at this and see this is asymmetrical because it's not evenly distributed around that sulfur. It's kind of bent around it. That makes sense? It's like, let's say this is a tire, okay, on the ground. We tie a rope to it in two places, and one guy's going to pull it this way and one guy's going to pull it that way. What direction does that tire go in? It goes in that direction. Okay, and that's kind of a simple way of explaining what's called vector addition. So the actual dipole moment for the molecule lies in this direction because the polarity goes in this direction. Okay, if you take physics, you'll be learning about vector addition. If you take higher level geometry, you'll learn about vector addition in a more complete way. Okay, there are actually mathematical and geometric ways of figuring out vector addition. All right, but we're only doing it just by looking at, well, what's the result, you know, in your mind. We're not going to try to go through teaching you vector addition. Just don't have time for that.
Do you mind explaining that one more time?
About why this is going like this?
Yes, why the arrows are going the way that they are.
Well, first of all, we have an electronegativity greater than 0.5. If the electronegativity difference. If the electronegativity difference is greater than 0.5, then we have polar bonds. This arrow with a plus sign on one end shows a polar bond. Not the whole molecule, just the bond. Okay, just this part down here shows the bond. Just this part shows the bond.
So that's why they're pointing out? Because
they're pointing toward the atom that has the greater electronegativity. Fluorine has a greater electronegativity than sulfur, so the arrow points toward fluorine. Okay? And because the greater electronegativity goes in this direction here and this direction here, the overall electronegativity for the molecule is kind of mix those together and going in that direction. Because you can't. If the definition of polarity is that one side of the molecule has more electronegativity than another. One side of the molecule has a partial negative charge and the other doesn't. So the definition of electronegativity itself is that it's a relative measure of how hard atoms pull on the electrons they share with another atom. So we're sharing electrons between sulfur and fluorine, as we show right here. Okay? But the electronegativity here tells us that fluorine is pulling on the electrons more strongly than sulfur is, because it has a greater electronegativity. Those electrons in that bond are being pulled more toward the fluorine. So, as a result then, the electrons are spending more of their time over here. Okay? Fluorine is winning the tug of war. Well, if there's more electrons more of the time around the fluorines than there are around the sulfur, this end has more electron density. Since electrons are negative, this end of the molecule up here is more electronegative than this end of the molecule down here. We show that with a partial negative charge and a partial positive charge. Okay? So you could show your polarity like this. But you have to show there's polarity in the bonds, and somehow you have to show that there is a polarity in the overall molecule. Okay? Somehow you have to say or show there's polarity in the molecule. So that really goes with either this or your justification, or somehow you draw it out. Huh? If they show this, that would be saying the molecule is polar. Okay? All right. Somehow, they have to show the bonds are all polar. Okay? And somehow they're going to have to show that you got a polar molecule when you're done. Does that make sense to everybody? Yes. Okay. All right. So this whole thing is worth 3 points if you get it right. Got it? All right, then let's go to number 6. CH3Br. So hydrogens all have one valence electron. Carbon has 4. Bromine has 7. If we do the sharing arrangement, these are electron dot notation for each of the 1, 2, 3, 4, 5 atoms in this molecule. This is electron dot notation for bromine, electron dot notation for chlorine, and 3 electron dot notations for hydrogens because there's 3 hydrogens. And we're going to do the sharing arrangement by sharing electrons in such a way to give all these atoms all the electrons they really want. Hydrogens share another electron to be like helium, the next highest noble gas, to stabilize the hydrogen. Carbon has 8 electrons now by sharing to be like neon, its next highest noble gas. And bromine has 8 electrons now by sharing an electron with carbon in order to be like krypton, its next highest noble gas. Now we're going to squeeze the electrons between the atom symbols to come up with a Lewis dot formula. So here's our Lewis dot formula. I've taken the electrons that are shared between the atoms and squeezed them in between those atom symbols. Okay? Since I now can see that I have 4 sets of electrons around an atom of interest or central atom, I know I need a tetrahedral. So an electron pair shape starts out as a tetrahedral. Okay? Then the next thing I'm going to do is replace any shared sets of electrons with the atom symbol they're shared with. And it doesn't really matter which end you put the bromine on. I'm going to put it on the top. Okay? And we've gotten rid of all the lone pairs, so now this is the molecular shape. This molecule is a tetrahedral. Okay? So the question is the polarity asymmetrical? Okay? We can see that the molecule is symmetrical. Same angles all the way around. But we don't know about the polarity yet. Alright? If it were all hydrogens around the outside, the molecule would be symmetrical. It wouldn't matter what the bond is because no matter what you have, you're going to have a non-polar molecule. But because we have a different kind of atom up here, we don't know yet. We've got to figure out the electronegativity for this bond and for the carbon to hydrogen bonds. So the electronegativity for bromine is 2.96. The electronegativity for carbon, look at the carbon to bromine bond here. Carbon is 2.55. And I find the difference 0.41. So that's the electronegativity difference for a carbon to bromine bond. And this is nonpolar. Okay? So this bond is not polar. I cannot put an arrow here. That dipole arrow like I used right here is only used for polar bonds. And for this class, we said that any electronegativity difference that's 5 or less is considered nonpolar. Okay? And let's look at the carbon to hydrogen bonds. Electronegativity for carbon, 2.55. The electronegativity for hydrogen, 2.1. Got an empty slot there, 0.45. Round off to 5. And I get 0.5 as the electronegativity for a carbon to hydrogen bond. Okay? Now we've called that nonpolar in here. Okay? Could call it polar. It's right at that break point. Okay? You could actually justify this molecule insofar as what we learned in this class. You can justify this molecule being nonpolar or polar. All right? We just haven't gone far enough down the road to learn about polarity to really know yet. Okay? But we're going to assume this to be nonpolar right now.
Why did you separate it?
Because I got two different kinds of bonds. Is that what you mean here?
Yeah.
I've got a carbon to hydrogen bond. I've got a carbon to bromine bond. Two different kinds of bonds. All right. Did anybody classify this bond as being polar? Okay, then we're all in agreement. All the bonds are nonpolar. Okay. So they have to be able to show the shape of the molecule. The bromine could have been on any of these arms. All right? Doesn't matter which arm, if you want to call it that, the bromine is on. Okay? They have to have calculated the polarity of both types of bonds somewhere. So those are both 1 point. And they have to classify the molecule as being nonpolar after doing all that. Okay, so this all together, this whole thing is going to be worth 4 points. Having said that, let me show you another way to think about this. Okay? Y'all got this? Since the hydrogens down here have an electronegativity of 2.1, and the bromine, which we could think of as being on the opposite side of the molecule, has an electronegativity of 2.6, the difference between 2.6 and 2.1 could make this a polar molecule, because the hydrogens are all down here and the bromine's up here. That's really a better way to do it, but that's not the way I've taught it so far. Okay? You with me? All right. All right, but it sounds like nobody tried to do it that way. If you tried to do it that way, I have to give you credit for it because it's reasonable. Nobody did it that way, right? What? Saying that it's polar and justifying it the way I just said. Because all the hydrogens down here have an electronegativity of 2.1, and the other side of the molecule, the complete other side of the molecule, is a bromine, which has an electronegativity of 2.6. If you subtract 2.1 from 2.96, you get 0.86, which actually rounds up to 0.9. If you justified a claim that this is a polar molecule using that math, I'd have to give you all the points. Does that make sense? Because they are kind of on opposite ends of the molecule. It's a reasonable justification, but nobody did that, so it doesn't sound like it. All right, let's go to 7, right? This is the one that isn't like anything we've done in here so far, so this is extra credit if you get this one right. Seven is boron tribromide. How many electrons are on a bromine? A boron? 3. How many electrons are on a bromine? Not 5. 7. 1, 2, 3, 4, 5, 6, 7. And I've got 3 bromines. All right. Based on what I've taught you so far in here, there's only one way to make this happen, and it's going to break a rule. Okay? Okay? So, there's no, given what I've taught you so far, there's no other way to make this happen. And what's the rule I broke? You don't even know? Really? Okay, so far we said anything above the first primary energy level, any of the elements that are beyond the first row want to have 8 valence electrons like the next highest noble gas. And boron doesn't have 8 electrons like neon. How many does it have? 6. And you can't get any more. Okay? No. This is the sharing arrangement. But I thought you could see that from what we did.
I did, but I didn't know if you made a mistake.
No, I just haven't gone that far yet. I wanted to... Alright? That's as far as you can go. You can't make 8 electrons. You can't just stick them on there from nowhere. It doesn't work that way. Okay? So how many sets of electrons do I have around this central atom? How many? 3 sets. What molecular shape do you get from 3 sets? Trigonal planar. Okay, that's a trigonal planar electron pair shape. I'm going to replace the sets of electrons with the atoms with which they are shared. Remember, there's always exceptions to every rule I give you. Okay? It's one of those things that just doesn't work out any other way. Okay? And no matter what you do, you're still going to come up with trigonal planar. Okay? There's a way to do some resonance, which I don't teach in a CP class. You still come up with trigonal planar. Any way you come about it, it's going to be trigonal planar. All right. This has symmetry. Has equal spacing. We didn't get rid of any lone pairs anywhere, did we? This is a symmetrical molecule. The bonds are all the same. It's not necessary to calculate electronegativity because no matter what I do, this is going to be a nonpolar molecule. It doesn't matter if the bonds are polar or not, because if the bonds are polar and they're all the same, it's like they equal out each other. It's like a 3-sided tug of war. You ever seen a 3-sided tug of war?
No.
Yeah?
It doesn't get anywhere.
Doesn't get anywhere. Okay? Alright, here's how a 3-sided tug of war works. Okay? You got 3 ropes knotted together. Okay? And you got 3 teams. And so the ropes, let me do this on a separate sheet of paper here. Here's our knot, and here's our 3 ropes. Okay? This team has to stay in here, this team has to stay in here, and this team has to stay in here. And whoever manages to pull the knot outside of this circle wins the tug of war. Huh? Huh? Well, if it goes out this side, they win. If it goes out this side, they win. If it goes out this side, they win. Whoever's on these ends of the ropes. Yeah, everybody's pulling just like a regular tug of war, 2-sided tug of war. Not really. What you actually do, you actually end up bisecting the circle like this. All right. So that if this knot goes anywhere over here, this team wins. If this knot ends up on outside the circle anywhere in here, this team wins. That's the way it works. Huh? Well, this is kind of like a 3-sided tug of war. Okay? Well, let's take a look just for the sake of looking at it. Let's look at the electronegativity here. Okay, we don't have to really, because we can see already it's symmetrical. There's no way. The bonds are all the same. The molecule is symmetrical. There's no way to have a polar molecule. Okay? Well, let's look at the electronegativity difference. And let's see, bromine is slightly higher than boron. I'll put it on the top. So the electronegativity difference for a boron to bromine bond is 0.92. So it is a polar molecule. I mean, it's a polar bond, not a polar molecule. So which way do the arrows go when I use dipole arrows?
It would go towards the BR.
Exactly. Toward the Br, toward the bromine. So that's our tug of war right there. The bromine's pulling the electrons in that direction, in that direction, in that direction, and nobody's winning. Like our tug of war, like our three-sided tug of war. Does that make sense?
What point does that get at? Like, where it wins?
Outside the circle, in either this quadrant, or not quadrant. What do you call it? It was only 3 parts, not a quadrant, but quadrant? I don't know. I don't know what it's called. Trident, maybe. I don't know. Okay? All right. Did anybody come up with the right molecular shape? No? You did?
You mean that molecular shape? Yeah.
Yeah. Did you come up with the fact that it's a nonpolar molecule? If you actually came up with that, and you have some kind of the reasonable justification here that it's, symmetrical, all the bonds are the same, or you show it somehow, you justify it, we're going to put 1 extra credit point on your paper.
I have a question.
Yes.
If one belongs to bodies, does that count?
What now?
If one belongs to bodies.
Oh, no. Then you made it trigonal pyramidal, and it's not trigonal pyramidal, it's trigonal planar. What?
If he just put the shape, is that something even?
He got this shape, but he didn't claim whether it's polar or not. That's not even the point of the exercise. The idea is to find out whether the whole thing is polar. So no, you get an extra credit if you claim it's nonpolar and you show one.
What if I claim it's nonpolar?
But you didn't show one.
I did this little equation.
Okay, fine. And I said you get a point on it.
I thought you said if it was 1.6 or higher is nonpolar. 1.5. Oh, wait, 0.5.
0.5 or higher.
0.5 to 1.6. That means polar.
Well, that's polar.
The bonds are polar, but the molecule itself is nonpolar. Then why is it nonpolar? Because it's not polar anyway?
Yeah. Yep. When he comes back, right when.
I thought it was polar.
So did somebody go to the bathroom? Came back? Okay. All right, listen carefully. Please listen carefully. The bonds are polar. But the molecule is nonpolar.
Why is that?
Because the polar bonds are evenly arranged all the way around. If we were going back to our original understanding of what causes polarity, these bromines are pulling on the electrons that it shares with the bromine more strongly. So there's a sort of a cluster of electrons here and here and here. Well, that's all the way around. There's no essential difference in the polarity if it's all the way around. The electron density is greater on the outside than the inside, but overall in the molecule that doesn't give you any positive or negative end. Okay? There's sort of an internal polarity, but that's not what we're trying to find. We're trying to find an overall external polarity for the molecule as a whole. And there is no polarity for the molecule overall. Okay? So, this molecule, because it's nonpolar, does not have a molecular dipole. Okay? This molecule, because it's nonpolar, does not have a molecular dipole. This molecule does not have a molecular dipole. At least the way I taught you to do it in this class. This molecule does have a molecular dipole. It's not the line, it's the fact why we put the line there. Okay? Alright, we said 8 and 5 were the same. So we're going to go now to number 9. Oh, let's see. This is extra credit. 1 point extra credit. If you showed the molecule being trigonal planar, and if you claimed it was nonpolar and justified that claim. What? It counts for you if you got it right. Doesn't hurt you if you got it wrong. Just extra credit. Really? Just extra credit. Okay. Be that way. Phosphorus trihydride. Well, when the shoe fits. Okay. Just a joke. All right. Huh? Then don't worry about it. It's like the O.J. Simpson trial. If the glove fits. That's it. What face is that? I've only got one. Alright, so it's a tetrahedral electron pair shape. We're going to replace 3 of the sets of electrons with hydrogens. And then we're going to remove the lone pairs. I hear a lot of chatting that doesn't have anything to do with chemistry. I wish you'd pay attention. I don't want to see the faces. Let's stay with this. Okay? Is it an asymmetrical molecule or not? Yes, it's asymmetrical. We had to remove a lone pair. Now, listen. If you can't look at that and see that it's asymmetrical, meaning not symmetrical, then you can drop back to, did I remove a lone pair? If I remove the lone pair, you know it's going to be asymmetrical. Okay? It's asymmetrical. Actually, it's 1s.
Mine looks a wee bit different than yours.
A wee bit. Just a wee bit.
Okay, do you have your hydrogen on the top or something?
Yeah.
It's fine. Okay. You can do that. Now look, asymmetrical molecules do not automatically mean you have a polar molecule. You have to know about the bonds. All the bonds are the same. Asymmetrical and all the bonds are the same. Don't tell you if the molecule is polar. You have to know if the bonds are polar. Okay? In addition to all that. Because what we're really looking for is not just asymmetry in the molecule, but asymmetry in polarity. Okay? So let's find out about the polarity of the bonds. Phosphorus has a greater electronegativity, I believe. Just barely. Electronegativity for phosphorus is 2.19. Electronegativity for hydrogen, 2.1. Got an empty slot over here. 0.09. I'll round off the 9, making the next digit a 1. And our electronegativity difference for a phosphorus to hydrogen bond is 0.1. Nonpolar. Okay? So we have an asymmetrical molecule, but we have nonpolar bonds. You cannot have a polar molecule if the bonds are all nonpolar. Okay? If all the bonds are nonpolar, it doesn't matter about everything else. If the bonds are nonpolar, if all the bonds are nonpolar, then your molecule is nonpolar. All right? Okay. So, to have a clearly justified answer, they have to be able to show the shape. They have to calculate the polarity of the bonds. Okay? And they have to come up with the correct claim that it's a nonpolar molecule. So that whole thing is worth 3 points. Got it? All right, number 10. Now this is also an example of why it's so important to make sure that all your letters are either all capitalized or lowercase and clearly so. This is carbon disulfide, okay? But if that S wasn't clearly a capital S, I would think it was a diatomic cesium, okay? It's very important that your letters clearly look like capital and lowercase letters, all right? All right, so carbon has 4 electron dots, sulfur has 6. When you put this together correctly, you get this kind of a electron Lewis dot formula.
Can you go back to number 9 real quick? I didn't, it was arrow before.
The arrows aren't pointing anywhere. It's a nonpolar molecule.
Wait, no, they are pointing somewhere.
Are you talking about dipole arrows or some other arrows? Because there are no dipole arrows in this molecule.
I got it wrong.
Dylan and Joseph, you think you might learn something by paying attention up here?
Yeah.
Okay. If I have 2 sets of electrons, remember electrons can be lone pairs. There are none on the central molecule. Sets of electrons can also be all the electrons shared between 2 atoms. So there are 2 sets of electrons here. What electron pair shape do you get when you have only 2 sets of electrons? A line. Linear it's called. Okay? So this is a linear electron pair shape. Now we're going to replace any sets of electrons that are shared with the atom symbol with which they are shared. And that gives us this. A linear molecule. Okay? This is, all the bonds are the same. It's symmetrical. Doesn't matter what the bond's polarity is. This is going to be a nonpolar molecule. Okay, so you can say this is nonpolar and say the reason is that it's a symmetrical molecule and all the bonds are the same.
What if they came up with non-polars that their thing is like a bent shape?
Well, bent's completely wrong. That doesn't justify anything.
Doesn't make sense?
Well, let's take a look at the electronegativity first and see if we can give them any credit for that. Since they did come up with the wrong shape, I'm not sure how they could do that, but they did. Sulfur has an electronegativity of 2.58. And carbon has an electronegativity of 2.55. So our electronegativity difference is 0.03. It's a carbon to sulfur bond. Non-polar bonds. So if they came up with the wrong shape, but they said it has non-polar bonds, and that was a justification for claiming this was a symmetrical molecule, we're going to have to count off something, but I don't know what yet. That's what we do. Okay? So you have to come up with the right shape of molecule. That's a point. You have to say it's non-polar. 1 point. And really, that's all you have to have. So if they have the wrong shape but have non-polar bonds, then we can only give them 1 out of 2 points. Okay?
What is that? Like the difference? Is that a point?
Yes? Alright, let's go back through and add up all the points we got here, okay?
You don't get another point for the
Yeah, they did. Would it be 3 points?
You don't need it. You don't have to have it.
Okay, now go back and look at this one.
Alright, problem number 5 is worth 3 points. Problem 6 is worth 4, that's 7. Problem 7 was an extra credit. 9 was worth 3 points, that's a total of 10, plus the 2 points here, so the total homework points is 12.
That would be 100.
Yes, but you're going to put not 100, but 12 points. No, that's without the extra credit. So you can have more than 12 points. What? What? Okay.